vector quantities. Magnetic fields describe magnetic influence. So this sounds a little bit circular or tautological. And the reason for this is magnetic fields are fundamental in physics. They're not made of anything else. They don't break down into other things. They are one of the fundamental forces of the universe. And so you can't describe a magnetic field in terms of other things. You can describe what it causes and what its influences are, but it is essentially fundamental to the best of our knowledge. And so the rest of the sentence gets into the sources of magnetic fields, which are electric charges in relative motion. So if you have something like a proton or an electron zipping around, it has an associated magnetic field around it. And the one that is maybe more familiar in our day-to-day lives are magnetized materials, permanent magnets, which have an associated magnetic field they carry around with them. When we try to describe magnetic fields, sort of generally in sort of a qualitative sense, there tend to be sort of two aspects to it. One is sort of the classic field line diagram you may have seen before, looking like these, which tries to essentially draw out the vector directions of the magnetic field. And in some vague way, you can characterize the field strength by the density of lines in a given location. And so you have these kinds of representations which try to describe qualitatively the sort of the topology of the magnetic field, and then the more simple measure of a magnetic field is usually the strength of the magnetic field. And so this is the one that we can get a sort of the easiest handle on. And so I've prepared this scale for throughout today's talk to try and characterize magnetic fields in different environments by their strengths so that we can compare them. And so my reference magnetic field is always the classic refrigerator magnet, which is strong enough to hold itself, in place against gravity, but you don't really notice a whole lot of other magnetic effect. And so we measure magnetic field strength in physics either in units of Tesla or in units of Gauss. Astronomy tends to use Gauss, and so that's what I've used throughout this talk. But
Cameron,
they're big. Yes.
Sorry to interrupt. Are you changing slides, or are you at the first slide?
Yes. No, I've been moving through slides. Have you not seen them?
I don't think slides are changing for me. Is it for you guys?
I see. Okay, let me adjust the screen share.
No, the slides were not changing. It changed right now. It's on the scale of magnetic field strength.
Yeah.
Okay, so something has gone wrong with my streaming. Allow me to reset. It might be easier if I just share my entire screen. So, okay, so if you guys haven't seen this then, I can sort of go back.
Now we can see the mouse and all.
Yeah, okay. So basically, most of this is just simple visuals. So magnetic, vector fields.
Also, Cameron, can you move to the first slide? There was something I wanted to ask.
So the very first slide here?
Yeah. Here on the right-hand side, we see contour lines representing the magnetic strength. Or is it representing the magnetic vector too? Or is it just a strength?
Yeah, so in this diagram on the right, are you seeing my mouse now, actually, now that I've changed the sharing mode?
Yeah.
Okay, yeah. So the short answer is that these are a proxy for the magnetic vector, except that they don't have a direction. And so we can't actually, based on the nature of these observations, we can't differentiate between a field sort of going inwards or going outwards, essentially. I'll come back to this. I guess this is later in the talk when I talk about what this data is and how we get it a bit. But
Cool.
Yeah. Okay. So unfortunately, you missed all the visual aids in the first few slides, but there wasn't much. Just as I said, sort of I got into it from public talk. I visited the VLA, did my PhD, magnets. So I'm glad that you pointed that out as early as you did. Magnetic fields through these kinds of magnetic field line diagrams. So basically it brings us back to where we were, which is different kinds of magnetic field strengths for context. And so I put a few examples here of the kinds of magnetic fields that we could encounter sort of on Earth, sort of in different environments. And so fridge magnets are about 50 Gauss. If you were to take apart a speaker, there's usually a very strong magnet in there. Or if you buy one of those really neat toy neodymium magnets, which are incredibly strong. Both of those tend to be about 10,000 Gauss at the surface. And so those are considered strong magnets normally. And the strongest magnet that you might typically encounter in normal life is associated with MRI machines. MRI scanners have very powerful superconducting magnets, and those tend to go to operate at about 50 kilogauss or 50,000 Gauss. And so this is sort of the range of typical magnetic fields you encounter. And I guess one side note I put in is household appliances also have magnetic fields associated with them. And occasionally you get people who are very worried about the effects of their electronics creating magnetic fields that could be affecting their health or something. But it turns out the magnetic field from household appliances is typically about 1,000 times weaker than a fridge magnet. And so there really is nothing to be afraid of in terms of the magnetic fields from electronic devices, because if that was enough to cause health problems, every fridge magnet would just be, a death trap, essentially. So briefly, I just wanted to introduce the sources of magnetism, although I did mention this briefly already. The main one that we think of in our day-to-day lives, and if you say magnet to most non-physicists, the first thing they would think of is a permanent magnet, a material that holds magnetic properties effectively permanently. And so this is the process of paramagnetism or ferromagnetism that we associate with your sort of classic bar magnet. And ferromagnetism or paramagnetism actually has essentially no effect in astrophysics. We don't see these kinds of materials with significant magnetic fields throughout astrophysics. And so what we do actually see, although it may seem surprising, is electric currents as the other source of magnetic fields. And so if you run an electric current through a wire, it produces an electromagnet, a magnetic field, for as long as the current is running. And it turns out this is what we see in astrophysical environments. We see naturally occurring electric currents as the source of magnetic fields throughout the universe. And so that was essentially the physics introduction to magnetic fields. So are there any questions on that before I jump into the astrophysics? Okay. So let's talk about space. And so what I was trying to sort of imply with these pictures is we actually do observe magnetic fields in all environments, from planetary scales, stellar stars, all the way up to galaxy scales and beyond. And I know I said we were going to start with the astrophysics, but that was a lie. We're going to start with the Earth. And so I think it's not surprising to anyone that the Earth has its own magnetic field. This is why compasses work. Compasses are reacting to the Earth's magnetic field. And the Earth's field has a lot of really interesting consequences for physical processes on the Earth that we may not necessarily always think about. The most famous of which is that the Earth's magnetosphere, the magnetic field around it, deflects solar radiation. So solar radiation in the form of charged particles stream away from the sun, approach the Earth, and are deflected away by the magnetic field. Pardon me a sec. Excuse me. So solar particles are deflected away, and there's this sort of typical image that some fraction of solar radiation gets captured in the magnetic poles and gets funneled down towards the Earth's north and south pole to cause the Aurora Borealis and the Aurora Australis in the south. And it turns out this picture is not entirely correct. I took a course on magnetospheric physics as a master's student, and the professor there got very angry at all of these diagrams because this is not actually completely true. Solar particles do cause the aurora, but they don't get funneled down field lines like this. What actually happens is a much more complicated process where the particles that are deflected tend to get sucked in the back of the magneto tail, which is this region here. Solar radiation instead gets sucked in the back, gets transported from the sort of night side of the Earth, and then gets funneled into the poles, causing the aurora. It's a much more involved process, and there's a lot more complexity there to study. But it's not as simple as just the simple funneling of directly from the solar wind. There's a lot of other weird places where the Earth's magnetic field pops up. And so there's evidence now that migrating birds have some kind of inbuilt way of sensing magnetic fields in their bodies. And so different kinds of birds are able to sense the magnetic field around them and use that to judge where they are and use it to be able to navigate along their migration routes. And so this has been found in, for example, Canadian geese, which migrate from northern Canada down to the southern US and back every year. And so they do this in part guided by their magnetic field senses. And even more bizarrely, and I really love this example, apparently cows and deer can also tend to respond to magnetic fields. It's been observed that when cows and deer are eating or resting, they have this weird tendency to line up with the local magnetic field. And so they preferentially prefer to align with the magnetic field rather than in any other direction. It's not a strong effect, but it is statistically significant. And no one knows why. And so, this is just a bizarre example of something else that the Earth's magnetic field is causing. And so, to put the Earth's magnetic field in context, the typical strength in whatever room you happen to be sitting in on the surface of the Earth is about half a Gauss. And so, in this context, it's 100 times weaker than your typical fridge magnet, which makes sense because otherwise your refrigerator would stick to the Earth in a weird way, I think. And it's about 100 or 1,000 times stronger than the magnetic field from your household appliances. So again, if household appliances could hurt you with their magnetic fields, then just standing on the Earth would be pretty dangerous. So with that context, what causes the Earth's magnetic field? I already gave you the hint that it's not permanent magnetism. The Earth's core is not some giant iron bar magnet. But how do we get electric currents in the Earth? And so to dig into where the Earth's magnetic field comes from, we need to go into a particular specific branch of physics called Dynamo Theory, which is a subset of Magnetohydrodynamics, which is just a fun word to say. Magnetohydrodynamics. So magnetohydrodynamics is the study of the dynamics, the motion, of fluids. Hydro is not water in this case. Hydro here is just fluids. And in this case, it's specifically fluids that are magnetically reactive, or equivalently, they are electrically conducting. And so we have any fluid that is sufficiently sensitive or reactive to magnetic fields or to electric currents is subject to magnetohydrodynamics, and this includes both liquid metals. Metals have sufficient conductivity, of course, as well as ionized gas, aka plasma. So plasma is notoriously reactive to electric and magnetic fields. And so either of these materials, if they are in the presence of a reasonably strong magnetic field, will experience behaviors that you would not get otherwise, that you would not get just from regular hydrodynamics of materials. And so MHD, Magnetohydrodynamics, is a very interestingly complicated corner of physics. And so to give a sense of it, I put this slide in the public talk with no intention of describing the mathematics involved, other than scaring the public of, hey, look at all this scary math. But for you guys, I think I can actually spend a minute to talk about it a little bit. And so so this is essentially the set of equations that are involved in computing essentially the evolution of a magnetohydrodynamic system. I'll see if I can remember all of this. I haven't done a lot of MHD myself, but I think I can remember how this goes. So the first equation, this is, I think the continuity equation is the name for it. It's the conservation of mass. You essentially have a term for the flow of material and a term for material increasing or decreasing at a location. And so, if material is flowing into a location but not leaving, then it has to increase, and vice versa. Second equation is this is the divergence of current. So I think this is a statement of the conservation of charge. I think it must be, conservation of charge, with the assumption I think that charge is not allowed to build up too much, maybe. So this is basically saying if you have current, electric charges flowing into a point, they also have to be flowing out in order to balance out. Divergence of the magnetic field. This is one of Maxwell's equations. This is just true of any magnetic field. Divergence of the electric field is caused by electric charges. This is a statement that electric charges create electric fields. And then the curl of the magnetic field is related to the current. So this is the statement that currents create magnetic fields that spiral or circle around the current. And then finally, the curl of the electric field is related to the change in the magnetic fields. This is induction. Changing magnetic fields create electric fields. So this, these four are Maxwell's equations. And then finally, a statement on electric charge. This is a very specific case. I don't recall the details. Charge. I think this is charge imbalance created by material moving across magnetic field lines. That's the velocity cross magnetic field terms. This is material crossing magnetic field lines, creating charge differences. And then current. This is the creation of electric current by electric fields and conductivity, or by material crossing field lines again. When material crosses field lines, you get currents. And then the final one, this is Newton's second law. This is the force balance equations. This is the acceleration term. This is a steady state acceleration or flow term, pressure term, gravity term, the Lorentz force from current moving through magnetic fields. And I don't remember what the last term is off the top of my head. I think this is a viscosity term. This is viscosity. And so basically we have all of this physics going on simultaneously. And if you want to understand some system, you set up, some system, some fluid in some environment with some forces, you need to solve all of these equations, which are partial differential equations, for all time and all space. And these are very nonlinear, highly coupled partial differential equations. And so it's a complete mess. And for the most part, you can't develop analytic solutions to these equations. Is maybe for simple systems, yes, but not for really interesting complex systems. And so the general approach is you either have to study the behavior by looking at only the sort of simple examples, or you have to go to full-on simulations in general. And so MHD is tough, is the short version.
Cameron, can you move back the previous slide? There in the in this slide, in equation 2.18, over the left hand side, in the second term, it's U dot del. So what's that operator called? I've always seen del to be in front of
Yeah, I don't remember. It has a name, and I've completely forgotten. I want to say like advection or something, but don't quote me on that because I just don't remember for sure.
Oh,
But yeah, it's called something like that, and it is. I'm trying to remember. I mean, mathematically. Sorry, go ahead.
No, I was just saying like you are right. It's called advection. Yes.
Yeah. Yeah, and it's been long enough. I'm trying to remember. Like, I mean, as a mathematical operator, you just you apply the operator to whatever's to the right, and so you take the. Actually, do you? No, you can't because it's you can't take a gradient of or can you take a gradient of a vector? Maybe you can.
no, we can't.
It's been too long.
Gradient of a we are taking dot product on the left hand, like here u dot del. So we'll get a scalar, right? And then apply that scalar to a vector. So what's that called? Neko might be able to help us.
It's been long enough. I can't actually remember.
So
Okay, so
u dot del will basically be your ux del x plus uy del y plus u del use that del z, and you just do the partial derivatives of the vector u. That's all you have.
oh, okay,
Like think of it as
Yeah.
just partial derivatives, like sum of three partial derivatives.
I see.
Yeah,
And
that sounds right.
also in 2.14, we do include the displacement currents, right?
Yeah. So there are some terms here that have been dropped, and I don't. Yeah, it's been so long since I've looked at this. I don't remember what all the motivations are. And so yeah, there's a term. There's a term here that's been dropped for charge buildup, and there's a term, like you say, the displacement current term has been dropped, and so I don't remember what the motivation for that is, because these equations rely on certain assumptions have been put in place about. I think something about how you can't get large charge buildups, because I think there's usually an assumption made that if you have a large charge buildup, it tends to self-neutralize very quickly. If you have a positive and negative charge separation, you get an electric field flowing one to the other, and the charges just move because the conductivity is high. And so the electric field terms and this charge term here are some kind of like residual fields that small fields that can only exist created by. In this case, it's the U cross B force that gives you a weak charge separation, I think. But anyways, I did not intend this to be a detailed lecture on NHD because I don't remember it that well. Oh dear, I'm trying. I am interested to talk about it because I'm trying to remember. I'm trying to see how much I can dredge out of my memory from 10 years ago. I'm doing better than I expected, but anyways, yeah, this is find a proper textbook on MHD if you really want to dig into this. Yeah. So we can look at a couple of like simple cases at least, or maybe diagrams that approximate what happens. And so when coming back to the dynamo, so the idea of a dynamo is a system that increases the magnetic field strength over time. And so the sort of simplest schematic picture we can draw is this diagram of the so-called stretch twist fold dynamo, where you start with some loop of conductive fluid with a magnetic field. These are magnetic field vectors drawn in, looping around this loop of material. And then you take the material and you stretch it out and you put a twist in it, like a 180 twist, and then fold the two half loops back on each other. And the net effect is you still have the same amount of material. You've not added or removed material from the system, but you've doubled up the magnetic field. And then somehow, I don't know how the last step sort of gets rid of the twist, maybe through magnetic reconnection or some process. But the end result is you have the same amount of material, but you have twice the magnetic field in the end. And so a dynamo is a system that experiences this kind of operation where it, through some kind of motion, it's able to effectively amplify the magnetic field over time. And so we can sort of simplify this down to sort of three key ingredients, which is that you need a conductive fluid to carry the magnetic field and to carry the currents to generate it. You need some kind of cyclic motion, and it needs to be a motion that returns back to its initial state, essentially, so that the system can repeatedly keep going through whatever steps it needs to in order to continue generating the magnetic field. A system that can only run once and then stop is not going to produce a stable magnetic field over time. And finally, a dynamo needs an initial magnetic field to get it started. A seed field is often called, and this is and so dynamo processes don't create magnetic fields from nothing. That's a whole separate class of physical phenomena called magnetogenesis processes, and those are generally studied separately within astrophysics. As the question of the origin of the first magnetic fields is very interesting, but is not solved by dynamo processes. And so with this context, how do we get a dynamo in the Earth? And so the answer is that the inner material, the inner molten material, I guess technically it's not the inner core of the Earth is solid, but there's this outer core of molten material, which is very rich in iron, among other things, and so it does conduct. It is electrically conductive, and so it is a sufficiently conductive fluid. And because the inner core is hotter than the surface of the Earth, you get convection, where hot material near the inner core, hot molten material, will rise, cool down, sink back down again, and repeat cyclically. Just classic convection. And because the Earth is spinning, as these convective cells rise and fall, they undergo Coriolis forces. And so the Coriolis forces spin up these cells into a helical motion, as in the diagram here. And so the net result is you have this conductive material undergoing these sort of helical motions in the core of the Earth. And combine that with whatever magnetic field the Earth started with, those are the conditions you need to drive a dynamo. It is a configuration that does indeed amplify the magnetic field. And so thus the magnetic field of the Earth continues to be sustained billions of years later. And so this is not completely understood, of course. There's still a lot of intriguing problems, such as the flipping of the direction of the Earth's magnetic field periodically. And so there's a lot of interesting complexity that's sitting underneath of all of this. One sort of diversion I just wanted to make, because I think it's really cool, is Dynamo experiments that are being done. And so this is not just a sort of theoretical science, crunching through the equations. This is also an experimental science of trying to create physical dynamos to see if they operate as expected and see how well they work and under what conditions they work, etc. And so this is a picture of one such experiment at the University of Maryland. This is a chamber. I think it's about 2.5 meters tall, if memory serves. So it's a little bit bigger than a human being. And inside of this sphere is 12 tons of liquid sodium. And so liquid sodium is electrically conductive. It's a suitable material for a dynamo. I think it's used because some of its properties, like its viscosity, temperature, conductivity, and such, are better suited for these experiments than something like liquid iron or other kinds of liquid metals. And so in order to create a dynamo, they spin this entire chamber, and with the entire 12 tons of liquid sodium, they spin it at 50 revolutions per second. And so you can imagine just how much rotational inertia this must have when this thing is spinning up. It's incredible. And they're able to get dynamo action and measure magnetic fields being amplified inside. And I was at a talk on this experiment a bunch of years ago, and they emphasized the challenges of these experiments in terms of the safety. And so imagine 12 tons of molten liquid sodium, incredibly hot, hundreds of degrees hot, Imagine if something ruptured in this chamber as it's spinning at 50 revolutions per second. Just incredibly hot sodium everywhere, setting everything on fire. And then imagine that this was in a building with a normal sprinkler system. Do you guys remember what happens when sodium comes into contact with water? Boom. And so, in principle, if anything goes wrong, and if there were, to set off sprinklers, this could be the biggest bomb in Maryland, essentially. And so what they've had to do is they've had to set up this experiment in its own separate building with no water anywhere in the building, no bathrooms, no kitchen, no nothing, and also completely swap out all the regular sprinkler systems with, I think, foam and halon gas and other kind of inert substances. And so I think they have halon. So if anything goes wrong, if the fire alarm gets triggered, the whole building fills with halon, and you have to get out of there while you still have enough oxygen in your lungs. And so it's a little bit of a dangerous experiment, but nothing has gone wrong so far as I'm aware. It's just a backup system. But this is the challenges of experimental physics, I suppose. But all right, we're half an hour in and we've not even gone to space yet. So let's talk about space. Let's talk about Jupiter. So I've already given you a hint that the Earth's magnetic field causes aurora. And so if I told you guys that we see aurora-like phenomena on Jupiter, that's a pretty big clue that we've got magnetic fields going on, isn't it? And sure enough, Jupiter has some crazy magnetic fields, really, really strong. And in this case, the aurora, and this is actually ultraviolet aurora. So this is an ultraviolet image of the aurora composited onto a standard visual image of Jupiter. And turns out the cause of this aurora is not solar radiation like it is on Earth. It's actually charged particles being ejected by Jupiter's moon Io. And so Io sits within the magnetic field of Jupiter, and Io is very famously volcanic and has a lot of extreme processes. And so it's spitting off material that becomes ionized, and that ionized material gets funneled by fields down to Jupiter's pole, causing this ultraviolet aurora. Jupiter has this enormous magnetic field, all kinds of physical processes going on. This is a radio image of Jupiter composited on the optical image. And so what we're seeing here is radio cyclotron emission being produced by particles trapped in Jupiter's magnetosphere, producing radio emission at very, very low frequencies. And it's incredibly dynamic. And so these three pictures are, I think, a couple of hours apart. And sort of, the shape and the intensity changes radically on timescales of only a couple of hours. And this is not even the full size of Jupiter's magnetosphere. This is just the inner region. The full size of Jupiter's magnetosphere is such that if you could see the magnetic field on the sky from Earth, it would look bigger than the moon, despite how much further Jupiter is away. And so it stretches out, I think, hundreds of times Jupiter's diameter across the solar system. It's absolutely enormous, and a lot of complexity. And so hopefully this should play. Hopefully it will capture my audio. This is a video using data from the Juno space probe, and there is some associated audio where they've taken radio signals as Juno flew past Jupiter, and they created a sort of audio analog to the radio signals, showing different kinds of interesting and weird radio modes. So hopefully you'll get the audio, which should start momentarily. Okay, too bad that didn't come through. So if you Yeah, that makes sense. Anyways, but yeah, if you guys just it's on YouTube, so if you just Google like Juno radio signal, you should find something later on. And it's um oops. Can I pause the video at the right spot? Yeah. And so basically just in this sort of waterfall diagram here, there's all kinds of crazy, I think they're called Whistler modes, where it's like changing pitch over the course of just a few hours and undergoing all kinds of crazy pitch changes, essentially, in terms of uh, the radio signals. And so this is over the course of just a few hours, 13 hours or so, and just dramatic changes in these radio signals. And so there's a lot of interesting complexity there to be studied. But and despite all of that, Jupiter's magnetic field is not actually all that different in strength than the Earth. It's about 8 times stronger at the surface. And so a lot of complexity, but not actually as crazy strong as you might have thought. But yeah, let's talk about the sun. So the sun has also a lot of crazy magnetic field phenomena. This is a representation of magnetic field lines on the surface of the sun, as measured using some, I think it's an ultraviolet instrument of some description, but they through some algorithm they were able to trace out the magnetic field lines on the surface of the sun at some point. And it is crazy and complicated and a complete mess. And so there's so much going on there. And so this is an actual image of solar eruptions or solar prominences at the surface of the sun, where material is essentially boiling off into space, but it's being trapped by magnetic flux tubes. And essentially, it's essentially being trapped to follow along magnetic field lines between different regions of the sun, and sort of bouncing between different areas on the sun. And so you get all of these kinds of really amazing, beautiful eruptions caused by the magnetic fields, essentially.
Can you give a scale, like how big these loops are?
Bigger than the Earth, for sure. I mean, in some sense, you can make out the curvature of the sun in this image, and so I'm not going to sit and do the full calculation, but I would put like the height of these things as, I don't know, a tenth of the radius of the sun. In which case, maybe you could fit 10 Earths actually underneath this kind of a thing. So yeah, the scale is significant, I guess. Like it's. I mean, yeah. If we go back to this image, in some sense, yeah. I mean, you can see loops here that are covering, a fair chunk of the distance across the sun. I think maybe not quite half the projected distance, but yeah. So I mean, definitely hundreds of thousands of kilometers, maybe bordering on 1,000,000 kilometers. Although, surprisingly, I think given given how extreme an environment the sun is, the magnetic field strength is not actually that crazy. It's about the same as the Earth within a factor of 2, basically. And so the sun's magnetic field under normal conditions is weaker than a fridge magnet, which is a bit weird to think about. But I have written normal here for a reason, and I can see that, yeah, Nekema is already, I think, caught on to this, which is there are more extreme environments within the sun, which is, of course, sunspots, comparatively dark regions on the surface of the sun. And it turns out that within sunspots, the magnetic fields are incredibly concentrated by about a factor of 3,000. And so this is, sunspots essentially are the strongest naturally occurring magnetic fields in the solar system. And so, you can immediately see, based on the position on the scale here, mankind has surpassed nature in terms of magnetic fields in the solar system, as we have created more powerful magnets than nature has, in the solar system. And I will come back to that caveat in a couple of minutes. Yeah, let's talk about the solar dynamo quickly. So the solar, like the Earth, we have to have a dynamo operating in order to sustain the magnetic field, and it worked differently because the configuration of the material is different and the motion of the material is different. And so in the sun, we get at least the dominant effect. It's this so-called alpha omega dynamo, where we have two different processes acting to stretch out the magnetic fields. The first one, this so-called omega effect, is differential rotation, where you start with some sort of north-south oriented magnetic field, and the sun is not spinning as a solid object, it's spinning faster at the equator than it is at the poles. And so the net effect is that magnetic field lines get pulled along at the equator relative to the poles. And so the equator, it gets stretched and stretched and stretched and stretched and stretched. And the net effect is what starts off as this north-south magnetic field quickly becomes wrapped around as sort of a spiral-like path, sort of much more azimuthal or toroidal. The second effect is weaker, but is essentially similar to the Earth in the sense that we get these convective cells of hotter material from deeper down, rising to the surface and dropping down again. And again, the Coriolis forces, which act to twist the path of these convective cells. And so the net effect is that if you start off with a east-west magnetic field, as these convective cells do their thing, it tends to drive the magnetic field lines towards a north-south configuration partially. And so together, these give you a cycle that you need where, an initial north-south magnetic field gets driven to an east-west configuration, and an east-west configuration gets driven to a north-south configuration. And so together, these give you amplification of the magnetic field. They give you a cycle that can sustain itself, albeit, not super efficiently, given that it's only a 1 Gauss field under normal conditions, but it works well enough to keep the whole system holding together.
Cameron, how long can this go on? Because as we have studied, according to Faraday's law, if a flow is creating some electric field or let's say a magnetic field, then the magnetic field itself will oppose the cause which is creating it, right?
Mm-hmm.
So sun wouldn't lose energy over some time, then stop doing
that. Yeah, absolutely. And so the dynamo does operate by converting kinetic energy into magnetic energy, and then the magnetic energy does dissipate away over time. And also the amplification process is finite as well, because is exactly what you said. When the magnetic field is created, it tends to oppose. You tend to get forces that oppose the creation of more magnetic field. And so all dynamo processes have a built-in saturation mechanism, where as the magnetic field gets stronger, it starts to suppress the motion of the fluid. I mean, because as part of the dynamo operation, the fluid has to move perpendicular or across magnetic field lines. And the stronger the magnetic field gets, the more it suppresses that motion. And so if you suppress the motion, suddenly you're not generating magnetic field. Therefore, the suppression is not getting any stronger. And so it does reach an equilibrium. There's a whole aspect of dynamo theory, which is trying to work out what is the saturation mechanism, how strong do you end up, where does the process stop? Because otherwise you'd be doubling the magnetic field, forever, and that would be unphysical. So yeah, you're absolutely right.
Also,
there is this mechanism.
Also, we have another question from Nekoma. So he's asking that, are solar storms essentially due to particle ejected during the breaking of the magnetic field line in the omega effect due to excess stretching?
That's a good question. I don't know, to be honest, as I do not actually have any specific knowledge about solar storms or coronal mass ejections or any of those solar surface processes. I'm trying to think if I've ever learned any details. I don't think I've ever come across any. It's not been relevant to my own work. But I mean, I would wager that magnetic fields are definitely involved at some stage, because you can get a lot of interestingly complicated phenomena like magnetic reconnection, where you do essentially get snapping of the magnetic fields from a very tangled configuration to a simpler configuration, and that can release a lot of energy. And so it wouldn't surprise me if that was one of the mechanisms for driving, huge energy release in solar storms. But yeah, that's me speculating wildly, taking the bit of physics that I do know and applying it to a system I don't understand. It's a bit of a dangerous thing
Also,
to do.
you talked about snapping of magnetic field. So what does snapping really mean? Isn't the magnetic field itself an abstract concept which we have created to interpret how a moving charge experiences a force? So what does snapping actually mean?
Yeah, so you've asked a bit of a philosophical question there about whether the magnetic field is a purely abstract thing. And I don't know that it is, because magnetic fields hold energy.
But the lines, the way we represent in
Well,
books
yeah, the lines are a representation of the field of the field topography, the geometry of the magnetic field. So the lines aren't real, but the field is. And I mean, the field, it has an energy density, it has physical effects, and so I think of the magnetic field as a real thing. The field itself is a real thing and not an abstract thing. The lines are abstract, certainly.
What about snapping of field lines?
Yeah, and so magnetic reconnection is a process that I don't understand either. Mostly because when I took a plasma physics course and a magnetospheric physics course years ago, and in both cases they kind of skipped over it because I vaguely remember statements to the effect that some of the assumptions of MHD break down when magnetic reconnection occurs. Is some of the assumptions about how you don't have charge separation or you don't have electric fields or something like that. And so basically the conditions become such that, I mean, my vague understanding is, from a macroscopic view, is that if you develop a magnetic field configuration where it's very complex and it would be a much lower energy state for the magnetic field to become simpler, whatever that means, then there's this reconnection mechanism where the magnetic field can essentially untangle itself and dump a lot of energy into the environment. And it has there are conditions about what the material has to be able, coupled to the magnetic field in a certain way in terms of strong conductivity, I think, and such like, and motions. I really don't know the details, but I know it's complicated. I know it's powerful.
Also, I think magnetohydrodynamics should break because we are doing calculus and all. And when something snaps, I think there should be a discontinuity, right?
The discontinuity is in the model, not in the physics. So
Yeah.
Magnetic reconnection happens on a finite timescale, but it is a very fast timescale compared to most of the magnetohydrodynamic phenomena. So you have some MHD system like the sun or something, and it has some characteristic timescale in which the magnetic field evolves. Could be days or whatever, and then or hours, and then the reconnection event may only occur in minutes. It's incredibly fast, and so that's also related to some of the assumptions breaking. And so it's not a zero time jump causing a discontinuity. It's simply a very rapid evolution, which is not described once you've simplified the equations by making assumptions. As soon as you break the assumptions, you break the equations. But that's a modeling thing, not a physical thing.
Also, you talked about time scales, like it's happening too quick for us to ignore it, right? So do physical theories have that kind of thing? We can differentiate between them. This this set of theories are more relevant towards very fast things. Like, are you getting me?
Not the theories, but the models.
Okay. So magnetohydrodynamics is a model.
Yeah, I think in principle you could try to do MHD with no assumptions built in, but I don't know if you could solve it, at all in some ways or straightforwardly. And so typically, I wish I had my textbook with me, but yeah, typically with magnetohydrodynamics is they make some standard set of simplifying assumptions. And so I don't recall what those assumptions are, but it's typically something like the system is not evolving super fast and conductivity is very, very high so as to be almost infinite kind of a thing. And so when you make those assumptions, it simplifies the equations to a point that you can deal with them much more straightforwardly. But as soon as you've made those assumptions, you've built in the problem that as soon as the assumptions aren't true, the model breaks.
Yeah. So has it happened like till now? Have you observed like anything which states something which against MHD, like our assumption?
Yeah. I mean, magnetic reconnection is a very classic example. In that
Okay.
standard MHD has no reconnection mechanism, and yet we know it happens, and we know why it happens. I just don't know because I've not studied it. But
No,
there's been a lot of
no
work
worries.
on it.
Yeah.
Yeah. So I mean, there's a lot going on. Yeah. Okay. So, as a bit of a brief diversion again, I wanted to introduce a little bit about measuring solar magnetism. And so there are a couple of different mechanisms, but the original one is through spectroscopy, and specifically through a physical effect called the Zamon Effect. And so this is an effect in quantum physics, actually, from atomic physics, where normally if you in an environment without a magnetic field, if you look at the spectra of atoms, spectral lines generally appear. You have some set of spectral lines, and if you take the same atoms and you put them into a environment with a magnetic field, it actually causes the spectral lines to become split, because it essentially changes the energy levels of different states within the atoms. The atom itself, the state of the electrons in the atom responds to the magnetic field and changes the energy, and that changes the transitions, which changes the spectral lines. And different atoms will experience different splitting into different numbers of lines depending on how many states were actually hidden behind one line. But the important property is that the splitting between these lines, and so the spacing of the lines when the Zamon effect is present, is proportional to the strength of the magnetic field. And so the stronger the magnetic field, the wider the lines split apart. And so it becomes, if you have an easy measurement, if you have the resolution to separate out the different lines. And the sun is, of course, incredibly bright, and so it's not hard to get a strong signal, and you can build an instrument that can resolve some of these lines. And so the earliest measurements of magnetic fields on the sun were from the Zamon effect, from essentially the atomic physics at the surface of the sun. And so I really enjoy this just as an example of atomic physics, physics of the very small, coming back to something as big as the sun and giving us leverage to understand it. And I'm not going to get into a lot of detail, but we know that other stars also have magnetic fields. We know this through Zamon effect measurements and other measurements. And there's a lot of work on trying to understand how dynamos work and how magnetic fields would be expected to work in other stars, particularly other kinds of stars. Like, we can ask interesting questions like, okay, some stars don't have very much convection, so how does that affect things? If a star has a very shallow convection layer, how does that affect the strength of the dynamo or the operation of the dynamo? Or Or the opposite, if we have a star that is convective all the way to its deep core, does that change the dynamo? Or does the operation of the dynamo change things in the core of the star? That's a question. And so there's a lot of work being done on that. And so this is the case where MHD simulations really start to become very important and very sophisticated. And this is a plot I pulled out of a paper. I don't remember what all is being plotted here. Some of it is magnetic fields, some of it is, I think, temperature fluctuations and convection and stuff. But people are developing these incredibly sophisticated simulations to try and dig into what's going on in trying to essentially generalize what we've observed in the sun into other environments. But yeah, we're not done with stars. Stars get a bit crazier, particularly neutron stars. And so neutron stars are the remnants of a dead star after it's undergone a supernova explosion, right? And so as part of the supernova explosion, the core of a dying star will collapse down from, star-sized, down to a few tens of kilometers across. And as it's collapsing, it's dragging the magnetic field with it. The magnetic field is tied into the material. And so as the material collapses, the magnetic field is becoming more and more concentrated as well. And so the net result is we go from a star with a magnetic field at the level of a Gauss or so, and as this star compresses down by factors of millions, billions, trillions in volume, the magnetic field shoots up to something like 100 gigagauss, 10 to the 11 Gauss. And so, yeah, so you have this amplification factor of 100 billion or so. And so this is, when I said earlier that, human beings have the strongest magnetic fields in the solar system, this is the exception. We are nowhere near this. And it doesn't stop there. And so there is a subclass of neutron stars that have even stronger magnetic fields. And I don't know why they're significantly stronger, but magnetars, these high magnetic field neutron stars, go up to a petagauss, so 10,000 times stronger than a normal neutron star will get you up to the highest level magnetar. And so that's an environment, yeah. I don't even, I'm trying to think how strong the Zamon effect would be in that kind of magnetic field. And it's like, can you even have atoms hold together in that kind of magnetic field? I don't even know.
Also, when we do spectroscopy, you talked about how we take set number of spectral lengths and try to fit it. Doing that in this kind of environment should be crazy, right? There would be hundreds of angstroms apart, right?
Potentially, yeah. I mean, I think, yeah, I don't know much about neutron star spectroscopy, but I think just the gravitational environment and such limits what kind of atoms you can get. And so, yeah, Nakoma said that they're just neutrons. I'm gonna put in a correction. The core of a neutron star has to be neutron degenerate matter, but a neutron star needs to have an outer surface. And so far as I know, the outer surface is thought to be conventional matter. That you have some kind of a shell.
It has iron crust, right?
I'm not sure, to be honest.
I talked to a neutron star researcher, he's doing PhD in neutron stars. He told me there's an outer crust and all. There's a nice Wikipedia page on this.
Yeah, there has been work on this, and I haven't followed it, so I don't know the details. But
also, do we have spectra from a neutron? I don't think so.
From an individual neutron? I mean, a neutron itself doesn't have a defined spectrum. Yeah, I don't know. I know there's been work on it. I simply don't know the details, and I know there is a lot of interestingly complicated nuclear physics involved, but that's the extent of my knowledge. Where was I? So yeah, and so neutron stars give us a bunch of really interestingly bizarre phenomena, and I've mentioned pulsars, of course, in my previous talk, but yeah, because we have these incredibly strong magnetic fields. Any ambient particles, ionized particles, will tend to be concentrated to the poles, again, to the magnetic poles. And there is indeed a aurora-like phenomenon, although it's not the same physics as terrestrial auroras, as auroras on Earth. So I don't know. There is a lot of active research being done on emission mechanisms in pulsars and neutron stars, and I don't know any of it. All I know is the net effect is you get particles, charged particles, a few. I think it's known to be something like 50 to 100 kilometers above the surface of a neutron star, and there's some process that causes them to create highly beamed radio emission. And so this is a crazy environment. I mean, neutron stars crazy enough on their own, of course. Their size is only a few tens of kilometers, and yet we've been able to figure out that neutron that the pulsar emission mechanism is caused like 50 to 100 kilometers above the neutron star. So that's like a couple of neutron star radii above. And so it'd be like if all of the radio emission on Earth were coming from the moon, kind of. It's kind of that scale. Is that maybe that's a little off, um, but it's pretty intense. Is it cyclotron? I don't think it's standard cyclotron, but I don't know why. I don't know. This is the limits of what I know. So you'd have to look it up because I think there have been papers written on this. I simply don't know. But
Also, Cameron, like these big field lines which we see, are there no frame dragging effect? Like these lines getting twisted up and all? Because neutron stars are spinning fast, right?
Some of them are, yeah. No, there are effects from that, and I also don't know what the side effects of that are. Yeah, I'm pretty sure there is frame dragging, and there's a lot of other interesting stuff going on. I can't remember the terminology that well either. It's been too long since I've talked to pulsar people.
Okay, no worries.
But yeah, it's a lot of crazy stuff going on, and a lot of work studying, the magnetosphere of pulsars as well. And so, yeah, because it's you guys, I don't need to introduce the pulsation mechanism as, how we receive the periodic signals from pulsars as they rotate. So, yeah. So let's talk about a subject near and dear to my heart, which is magnetism in galaxies. So magnetism does not stop with just stars. You don't need a solid object. And so we know that galaxies themselves are magnetized. And when I say a galaxy, what I really mean is the interstellar medium, all of the stuff between the stars, the gas, the dust. And by gas, I really mean plasma for the most part. And so, we're used to thinking about the interstellar medium maybe as all of these these very bright features, these big emission nebulae, and the dark clouds and stuff as well as that. But I mean, even in the areas of the sky where you're not seeing any particular glowy structures, the ISM basically just looks like this. It's blank. It's dark. It's too thin to show up, bright enough to really be seen. But there is always material everywhere throughout the galaxy, throughout interstellar space. And most of it's ionized, and that has some interesting consequences in terms of being able to carry magnetic fields. And so, what we can do, for example, now we're finally coming back to this picture from the front slide. If we look at a galaxy, this is M51, the Whirlpool Galaxy, and if we look at it with radio polarization data, turns out that is sensitive to the magnetic fields through synchrotron radiation. in particular. And so synchrotron radiation is created by magnetic fields, and it's intrinsically polarized perpendicular to the magnetic field. And so if you measure the polarization of synchrotron radiation and you just rotate it perpendicular to itself, 90 degrees, that's telling you the orientation of the magnetic field in the plane of the sky. So it's not telling you anything about magnetic fields towards or away from you, but the magnetic field in the plane of the sky. And so if you have a galaxy in the plane of the sky like this, you can map out its magnetic field in its disk, essentially. And sure enough, there are magnetic fields everywhere, and they are also complicated in the sense that they have spiral structure, but the spiral doesn't necessarily match up with the spiral arms of stars and gas and stuff. And so, we have the spiral structure, but it's not the same spiral structure. And it's weird in the sense that it's strong in some places and it's weak in other places. And there's just all kinds of stuff going on here. And it's not just the disk either. And so if you look at an edge-on galaxy, like I forget which one this is, but an edge-on spiral galaxy, the magnetic field's not just in the disk, it's stretching out into the halo above and below the disk in galaxies. And it's, again, got a very organized, coherent structure. In this case, this is the so-called X shape, where it has this sort of X coming out of the galactic center, or this curvature. And so this is a coherent pattern in the magnetic field on the scale of practically the entire disk. This is tens of kiloparsecs. And the magnetic field is coherent and organized. And yet it's not very strong. I mean, there's not a lot of material, so the whole dynamo process is limited in how efficiently it can run. And so the galactic magnetic field is sitting down at a handful of microgauss. So, we've now dropped by a factor of, 500,000 from the Earth's magnetic field? Something like that, a couple 100,000. So it's not a very strong magnetic field, but it is present throughout all of interstellar space. It's organized, and that's an interesting thing to think about, because this is a magnetic field stretches across an entire galaxy, 100,000 light years across, and yet it's held together and it's organized, even though the travel time of the gas around the galaxy is hundreds of millions of years. The travel time for light is 100,000 or tens of thousands, and yet the magnetic field retains its shape. And I think that's amazing.
Also, are dynamos at play over here?
Absolutely. You've anticipated my next slide. So yeah, there's a couple of different dynamos in play. So the one in terms of the large-scale operation basically works similar to the sun, except now we're in more of a cylindrical geometry. And so if you start off with sort of a radial magnetic field in and out, the galaxy is doing differential rotation again. It's spinning faster on the inside than on the outside. And so, that rotation will give you very naturally sort of a spiral configuration very efficiently. And at the same time, there is actually a form of convection kind of as well. And so what we get in the disk is supernova explosions that lift out enormous amounts of hot plasma and basically explode out of the disk and into basically, it's called a galactic fountain. And so you have this hot material bursting out of the disk, carrying magnetic field with it, and eventually it cools off and starts to collapse back down into the disk. But as it's doing this, it's carrying magnetic field. It's undergoing Coriolis or differential rotation forces, which are twisting it again. And so this does give you a bit of a twist. And then it sort of ends up carrying away part of the twisted magnetic field. And so the net result is you get a weak amount of radial, sort of in and out magnetic field. And so this is enough to give you enough of a cycle to hold a dynamo together, albeit a very weak one. And so this process basically sustains the Milky Way magnetic field on the very large scales, on the scales of the rotation, which is the whole disk, and on the scales of these supernova explosions, which end up being hundreds of parsecs across. There are other dynamo processes that I'm not going to get into, mostly involving turbulence. And so in addition to all this bulk motion, there's also sort of turbulent mixing as well. And that's also responsible for some dynamo action as well, because the turbulence, the motion of the turbulent plasma is affected by the magnetic field, and it tends to follow patterns that amplify the magnetic field over time. And so you end up with both this very large organized component, and then what's not shown here is also all kinds of little turbulent mixing on smaller scales down to sort of light years and below. So this is actually where my slides end. I just wanted to add one further comment, which is that this is not where the magnetic fields stop. And so there have been observations of magnetic fields in galaxy clusters, where you have many galaxies orbiting each other, and galaxy clusters are emitting gas carrying magnetic fields as a result of this galactic fountain process, for example. And so you have all of these magnetic fields, all this magnetic field carrying plasma being spewed into the intercluster medium of a galaxy cluster, carrying the magnetic field with it, and that can hold itself together for sort of billion-year timescales as well. I don't know whether dynamos operate within cluster environments. Maybe if it was anything, I think it would be a kind of turbulence dynamo, because there tends not to be, you don't have the same kind of organized rotation in a galaxy cluster that you do in a star or a galaxy. But you do get it on these galaxy cluster scales. That's been measured. And we don't have direct measurements of magnetic fields on the scale of cosmic filaments, right? So sort of like, filaments being collections of clusters and such. We don't have direct measurements, but we do have physical measurements that imply a lower limit, which means we know whatever magnetic field exists in sort of intergalactic space, the magnetic field has to be, there's some lower limit, it has to be at least that strong or stronger. And so we have those kinds of measurements, and we have upper limits. The intergalactic magnetic field cannot be stronger than this number. And so we have a range, but we've not directly measured the strength of the intergalactic magnetic field yet, although there's a lot of exciting projects, maybe in the next 10 years, hopefully. It's getting close. But yeah, so that's basically the end of the material I had prepared, where basically the main thing I wanted to get out there is that magnetic fields are everywhere in every astrophysical environment, causing some crazy stuff to happen generally in the background. And so any environment that you can think about or hear about in astrophysics, you can always ask the question, yes, but what is the magnetic field doing? And there's probably something interesting going on. So yeah, I'll end it there, and yeah, take questions. I see Nekama has a question. Is it possible to have magnetic fields in interstellar void? So that's an interesting question, in the sense that you can't. I don't think you can have stable magnetic fields, in the sense that you need a medium to essentially from Maxwell's equations. You have to have, if you have a magnetic field, that implies a current somewhere. And so, I mean, in some sense, you could think of, like, in the idealized case, you have a dipole magnet somewhere in the universe, and its magnetic field goes out to infinity, albeit infinitely weak at infinite distance. And so you could get some of that, in space. I mean, even interstellar voids, I guess, in principle, there is some. There has to be some material everywhere. Essentially, we know that, and so even in regions of incredibly low density, there is still a material, and that material can carry the magnetic fields with it, and so it's all probably out there. But I mean, the magnetic field as a vector field, I mean, anything that's non-zero, does that still count? At what point do you say there's no magnetic field anymore? 10 to the minus 6 Gauss, 10 to the minus 10, 10 to the minus 12. It becomes kind of an arbitrary thing, I think. But yeah. Any other
Thank you,
questions?
Cameron, for this amazing talk. I really enjoyed it. And I have a couple of doubts. So, yeah. So, in the last image, we have a galaxy, and you showed the contour lines and all the orientation of the magnetic field, not necessarily the direction, right?
Mhm.
So, do we have enough plasma to create this? Because isn't galaxy mostly non-ionized gases?
No. So the interstellar medium. So we definitely do have enough material. So the interstellar medium is about 5%, I think, of the baryonic mass, and so you can basically divide up the baryonic mass in a galaxy, the non-dark matter, as 95% stars, 5% interstellar medium, and some smattering of leftover, planets and such. And so that of that 5%, I think. Do I have the textbook with me? Oh, I have a textbook. Give me 5 seconds. Yeah, I really like. So this is. I'll try and hold this up for the camera. The physics and chemistry of the interstellar medium
Just
by
post the
Xander
link
Thielen.
in whiteboard. That would be great.
So this is an interstellar medium textbook I really like, and it has a table right in the beginning of different components of interstellar space and how much mass they have. And so I don't even have to do it from memory. I can look it up. And so by mass, here we go. So the hot, so we have the hot and the ionized phases, and the cold. So by mass, neutral material is about half to 2/3 of the mass, I suppose. And so so if we say 5% of the mass of a galaxy, and then we'll call it 60% of that is still neutral gas, so molecular or atomic gas, and so that leaves 2% of the entire mass of the galaxy as interstellar plasma.
Isn't that too less at a galactic scale?
Well, I mean, it's not concentrated, but it's. I mean, we know that it's enough to sustain a magnetic field because we observe the magnetic field. And so, I mean, you pose an interesting question in the sense that there were questions asked years ago that, hey, could this magnetic field in interstellar space just be magnetic field being carried off by solar wind off of all the different stars, right? If every star has its own solar or stellar wind, and that carries a little bit of magnetic field with it, is that enough magnetic field to fill an entire galaxy?
I don't think that would be so organized like this because stars are
Yep,
everywhere.
that's the counter. That's the counter argument. You beat me to it. So yeah, if you had 100 billion stars throwing off stellar winds, that doesn't give you a structure organized on tens of thousands of light years. And so this is the result of dynamo processes organizing the magnetic field and sustaining an organized magnetic field. It's the only way you can get this.
I see. Also, how we measure this magnetic field? You talked about radio polarization or something. I don't remember exactly, but can you go in more detail, how we do that?
Yeah. So in the case of a map like this is essentially mapping out the polarization of synchrotron radiation. So synchrotron radiation is created by the combination of cosmic ray electrons, which are come from supernovae and other extreme environments. Cosmic ray electrons scatter throughout the galaxy, and then they interact with the interstellar magnetic field to create radio emission. That radio emission has a very characteristic spectrum. Based on my previous talk, it's very bright at low frequencies in the low frequency radio regime. And what I didn't mention in the previous talk is that the synchrotron radiation is intrinsically polarized. It has a net polarization that is always perpendicular to the magnetic field direction where it's created. And so, it carries that polarization with it. And then when we observe it, we can measure the polarization at that time, although that's subject to a couple of challenges. So, for example, we have limited resolution, and so sort of this, for example, the circle here is sort of, this gives you a sense of the characteristic resolution, is we only resolve things that are about that big or sort of blurred by that amount. And so what happens is if the magnetic field changes direction significantly within that area, the polarization becomes averaged out. You get a process where the polarization, if you're adding together two opposite polarizations, they cancel out. And so in some of these empty spots like that, that's what's happening. This is a region where the magnetic field is changing direction significantly somehow.
So they are canceling out.
Yeah. So I mean, the magnetic field is still there. And so like if you do high resolution measurements, you can actually then you start to pick out the polarization again, because you can measure the different regions. But when you have really, really coarse resolution, you start to get cancellation. But so what you really measure is within whatever the area of your resolution is, what is the average magnetic field? Or you're essentially doing a vector averaging of the polarization, and that's kind of representative of a vector average of the magnetic field. And so, by definition, these kinds of measurements with the coarse resolution are measuring the large scale magnetic field, the bulk effect at the size of your resolution. And so in this case, the resolution is about, I don't know, 1 kiloparsec or so, I guess, or a few hundred parsecs. And so every measurement here is saying this is the average magnetic field on an area of a few hundred parsecs across times the depth of the galaxy, or averaged over the depth of the galaxy. So there's a lot of averaging going on in these measurements.
So these are essentially derived results from the radio spectrum, right?
Yeah.
We are essentially not measuring this directly, but these are derived from other measurements.
Yeah, it's radio polarization measurements, and then we say, okay, we understand the physics of synchrotron radiation, and we know that this measurement is synchrotron radiation because of the spectrum. Therefore, because we know that this is synchrotron radiation, we know that the polarization is related to the magnetic field in this way. And that allows us to make our derivation of the magnetic field direction and some amount of estimates of the magnetic field strength.
I see.
Yeah, there are other processes as well, which I didn't get into because of time, like Faraday rotation. I can't remember if I mentioned Faraday rotation in my previous talk or not, but
I don't think you mentioned that.
Yeah, that's a separate physical process where the polarization gets changed by a magnetic field between a radio source and us. I won't go into it today, but essentially we can measure how polarization gets changed by magnetic fields as it travels, and that tells us about the magnetic field along the path, essentially. And so, excuse me, we use that to study magnetic fields around in the Milky Way a lot, because we can look at radio sources like distant radio galaxies and then say, okay, we measured the polarization shift due to Faraday rotation, and then that tells us how the magnetic field in the Milky Way has to be configured. And so there are these other processes as well.
I see. Also, how much of a significant role does magnetic field play in the galactic structure or any astrophysical structures?
So that's a question that's been asked a lot, actually. And so there's been a lot of questions about, can magnetic fields affect rotation in galaxies, right? The rotation curve problem, because that's a big part of dark matter, ideas. And the calculation is always that they're just not strong enough to have an effect. And so the structure in a galaxy is driven mostly by the rotation, and which is a consequence of the gravity. And so there's some really good plots actually of the amount of energy associated with different aspects of the interstellar medium, and the energy associated with the rotation around the galactic center is something like 10,000 times stronger than everything else. Because the other sources of energy are turbulent motion, temperature, so thermal energy, magnetic field energy, stuff like that. And all of that is thousands of times weaker than the motion, than the orbiting, the orbital energy. And so the orbit, because it dominates the energy budget, it does its own thing. And so all of the spiral structure is its own thing, driven by gravity. But the interstellar, the interstellar medium, suddenly the magnetic field does have enough energy to affect things like the turbulence. And so we're starting to think more, starting to think more these days about how can the magnetic field shape the interstellar plasma. Like, does it start to form, for example, magnetic filaments? And so, coming back to the I was going to come back to the question in the chat. Now my screensaver kicked in. There we go. So it is really much kind of the reverse, where the rotation dominates the effects in the magnetic field. And so you get, for example, this omega effect in the dynamo, where the rotation, the differential rotation, winds up the magnetic field. And so the rotation supplies some of the energy to hold the magnetic field together. Because the dynamo process converts some of the mechanical, the kinetic energy into magnetic field energy as part of the process.
Also, like, what about the first light of magnetic field? Like, by the first light, I mean, like, we have rotation, like what Neko said. We have rotation that's partially affecting the magnetic field, and our magnetic field partially affecting the rotation. But as effects are too small, we ignore that, right? Like we have galactic rotation that's affecting our magnetic field, or galactic or plasma motion, which is essentially generating the magnetic field, and magnetic field is also interacting with that, right? The same gas which is producing it due to Faraday's law. So when did it all start? Like isn't it looping back to itself? Like
there is some amount of feedback. The magnetic field can't meaningfully affect the rotation, but it can affect small scale motion, turbulence. So there is all of that is feedback effects, and so that's part of what makes all of magnetohydrodynamics to be very nonlinear, in the sense that you do have these feedback effects, and so the end result has to be some kind of a balance or a stable configuration where the effects balance out without destroying each other.
I see. Also, on the last question, like, why should we care about like magnetic fields? Like, it looks all cool and like, yeah, it's pretty cool, but why should we should focus on this? Like,
what I didn't necessarily show a lot of is cases where the magnetic field does change things by quite a bit. And so the magnetic field does tend to pop up in problems where systems that there are a lot of systems that can't necessarily be well understood without the magnetic fields. And so one example is protostellar collapse. And so you start off with molecular clouds that collapse to form new stars. And part of that process is that, as part of the collapse, there is a fight against the magnetic field, trying to hold things apart to a degree. And so there's this net effect of the magnetic field adds a pressure component, or sort of a virtual pressure, when these protostellar clouds are trying to collapse. And so you can ask interesting questions like, okay, can this slow down star formation if there is a significant magnetic field? And so what role does the magnetic field play in star formation? Does it slow it down? Are there ways it could speed it up? Because there's also some ideas for that as well, where the magnetic field can funnel material in faster than it otherwise would. And so what is the net effect, and how does this change our ideas for how efficient star formation can be? Which also plays back to how the earliest galaxies formed, because a lot of the structure of the earliest galaxies tied back to the efficiency of star formation. So that's one example. But yeah, there tend to be a lot of these knock-on effects where the magnetic field will do something, and then that'll change something else, and that'll change something else. And so, to understand the system well, we need to dig in deeply enough to know the magnetic field as well.
Okay. Also, you talked about pressure created due to magnetic fields. How significant is that in a star which is there, it's formed?
Yeah.
So how
No,
much
in a
about
star, it's not a significant effect at all. But this
okay.
is in the very early stages of cloud collapse, where you'll have these molecular clouds that are still hundreds of light years across. So they're still low density, but particularly in the molecular clouds, the magnetic fields tend to get enhanced compared to interstellar space, and so then the magnetic fields can start to matter at a significant level. Not deciding things, like the magnetic field is not 100% guiding things, but maybe at like a 10% level, where it's like, okay, the magnetic field can change this by 10% or 20% or something, and that's enough to maybe be interesting for modeling.
I see. Yeah, so that's all from my side. Sorry for bothering you for
No,
so
those are
long.
good questions. But yeah, any other questions from anyone else?
Yeah, I guess I can ask something. So my understanding is that the origin or the formation sort of mechanism for these galactic magnetic fields is, if I recall correctly, supernova, or not?
So that is an interesting question. So the method of essentially keeping the magnetic field is dynamo processes in interstellar space, and supernova play a role in that by driving the fountain effect, basically. But the origin of sort of the first magnetic field as the galaxies are first getting started is not well understood. There are competing theories because you need different physical processes to generate sort of magnetic fields sort of from nothing, or starting from no magnetic field and ending up with some magnetic field is actually surprisingly difficult to do physically. And so there are a couple of processes that I've heard about, which mostly involve stars, actually. And so the idea is that you get the first magnetic fields from stars, and particularly like ultraviolet light in certain conditions can drive weak magnetic fields. And then as soon as the early stars produce a little bit of magnetism, and then spread that to the interstellar medium through solar winds and stuff, then basically the galaxy grabs what little magnetic field it gets from the stars in the very early universe, and then the dynamo runs and picks it up and amplifies it to strength we see today.
Should we expect some more concentrated regions of, magnetic field strength on the young supernova, or is there like no correlation there?
I mean, so we do expect supernova remnants. I mean, we observe supernova remnants have amplified magnetic fields, but I don't think that's due to anything in the supernova. That's more it's shock compression, essentially, because the supernova shock wave, right, it's blowing out, and it's sweeping up all of whatever gas was flying around, floating around before that, and whatever magnetic fields were present in that interstellar gas before the shock wave blows through. And so the shock wave is basically gathering up everything into one area, and that amplifies the magnetic field. It concentrates it. And so we do see supernova remnants have these really strong magnetic fields along sort of the outer bubble of the supernova remnant from that sort of shockwave collection effect.
Oh, cool. That makes sense.
Also, Cameron, can you if you we have overshoot by 1 hour, so if you
I have
still
nowhere
have
to be. It's fine.
you have to go now.
No, I'm fine for the
Oh,
time being. So.
okay. So can you talk more about how the auroras form and how the electrons or cosmic ray particles are funneled into? So
Nice.
from a perspective, we know how force act on a moving electron, right? F is equals to Q cross V. Q into V cross B, right? So from that perspective, because I never understood like how someone like an electron is coming from this side and the magnetic field looks like it's anti-parallel to it. Okay, so how can it experience any force? Right, from like a vector force and all.
Yeah, let me think here. It's been a while since I've worked on this. Yeah, I mean, I guess first thing to keep in mind is that the magnetic field lines that are drawn in are not the end of it. There are there are more magnetic field lines. And so, for example, in this bow shock environment, there will be magnetic fields here as well. And so what you essentially have is solar particles crossing perpendicular to the magnetic fields. And so they are so yeah, I mean, when you say, the Lorentz force as sort of V cross B, how that manifests is whenever you can think of it as whenever a charged particle crosses a magnetic field line, it experiences force, right? That's an equivalent way of expressing that. And so as the charged particles are coming in, they're crossing the magnetic field lines in the front, and so they're experiencing a force to the side. And so because there is actually a sort of a circular symmetry in front of the Earth, that force to the side has the net effect of deflecting them away from sort of if they were traveling directly towards the Earth.
Okay.
Yep. And so that's essentially the net effect. I mean, yeah, to some degree, because it's a force whenever a particle crosses a magnetic field line, it has the net effect of essentially guiding charged particles to go along field lines.
Like the first bit here, you told that particle will feel a force that's perpendicular to it, so it will move away from the center. But how is it funneling down? Like, isn't the force applied over here is anti-parallel to the motion, or parallel, whatever the arrows are there?
No. So in this case, there's no actual acceleration downwards. There's no acceleration. What there is any velocity perpendicular to the magnetic field lines tends to get redirected around. And so rather than being accelerated downwards, it's more of a particle is going through, and then it's not lined up with the magnetic field, so it gets deflected sort of circularly around,
spiral way.
And then it's it's again not parallel, and so rather than having a straight line like this, it's more of a spiraling in. And particularly as you get closer and closer in, the magnetic field is getting stronger, and so the spiraling effect essentially gets stronger. It becomes increasingly confined.
Also, can you talk a bit more about the compression of the magnetic field on the front side and how it's why the shape is like this?
Yeah, that's a good question. Let me think about this for a second here. Yeah, I'm not sure I could give a good description of it in terms of something like the current configuration and how any currents involved affect
Because my
it.
argument is that the origination of the magnetic field is inside the Earth. So how the external field lines are getting morphed by how the particles are coming from the sun? Is it that these solar winds are also carrying their own magnetic field and they are interacting to produce a net magnetic field?
So that is part of it. Yeah, there are magnetic fields being carried by the solar wind.
Okay.
I think another way of interpreting it is that the solar wind is carrying currents with it, right? It's charged particles. Charged particles are being accelerated and moved around, and so there are currents associated with all of this flow in the solar wind. And in some sense, coming back to the Lorentz force, I guess, is the currents are such that it is countering in some ways the magnetic field of the Earth. And so there is a I've lost the term here, but essentially a counter magnetic field is being generated by the currents in this region, and that counter magnetic field is compressing or fighting against the Earth magnetic field in this environment.
So the red line is the net magnetic field at that point, right?
I think so. Yeah, that's how I think of it. Yeah, I mean,
Also, how
and
we
on
have
the other
measured
side of the Earth.
Yeah, go on. If that's the
I was
case.
going to say on the other side, I know that there are currents in the plasma of the Magneto tail here. I mean, this was a big part of my magnetospheric physics class from 10 years ago, which is talking about currents in the tail, and how that essentially the currents in the tail essentially generate magnetic fields that give you sort of a net. It has the net effect of essentially stretching out the field lines. It's creating a magnetic field that has the right kind of rotation or handedness to it to stretch it out.
Also, how
Sorry,
we
what was the
measure
question?
this? How we measure this?
Yeah. So a lot of it is done by satellite missions these days, and so my original university, Calgary, has a very strong space physics group, and they do a lot of work with satellite missions where you send up a satellite, and you can measure the local magnetic field at any point. You can measure particle population, particle flux, particle energy, to see, and particle direction. Actually, you can even measure what direction the particles are traveling at, and so you can send out satellites and essentially map out, huge parts in the magnetosphere that way. And then from there, a lot of it is also modeling based on the application of plasma physics. So things like the property that charges tend to follow along magnetic field lines, and there's limitations to how much particles can cross magnetic field lines. And so you can use those those physical laws as well to fill in the bits that you have not directly measured. So you take the parts that you have measured and then fill in the rest with models.
I see. So that's all from my side.
I had one small question.
Mm-hmm.
So for the galactic magnetic fields that we were talking about, since galaxies tend to have a flat rotation curve,
Mm-hmm.
the way you talked about like how a dynamo forms basically is due to the differential speed at different radiuses of the universe, of the of the galaxy. So is it possible that some galaxy doesn't have enough speed to create a dynamo effect and hence has no magnetic field?
Yes, actually. So we observe that elliptical galaxies have very weak magnetic fields because they don't have the level of bulk rotation or bulk motion. Right, elliptical galaxies tend to be a lot more turbulent, a lot more messy, and so we just don't see organized magnetic fields on large scales in those galaxies. And the same also goes for dwarf galaxies. So dwarf galaxies aren't big enough to have much in the way of organized rotation in some cases. Depends on the size of the dwarf galaxy. But dwarf galaxies also tend to be gas poor, if memory serves. And so you need the gas, the plasma as well, to be the medium that operates the dynamo. And so a dwarf galaxy that doesn't have much gas in it simply can't sustain a very strong dynamo at all, even if the rotation is there.
So have you? So we have observed these kinds of galaxies, right?
Yeah, absolutely. And so yeah, like we've done a lot of observations of different kinds of galaxies. That was actually a major part of my master's thesis, was looking at. My master's was mostly spiral galaxies, but I know that there have been other groups. I know I have colleagues that I've worked with who do dwarf galaxies specifically, and they've done a lot of work on those and a lot of different observations of different kinds of dwarf galaxies.
And the predictions of dynamo theory have worked out perfectly for these galaxies as
well. I wouldn't say perfectly, no.
Oh, okay.
Oh no, it's a mess. It's a real mess. I mean, my master's thesis was comparing dynamo models to spiral galaxies, and oh god, it was so bad.
So, like, what did you come up with?
Mostly, I think. Well, that's a whole talk of its own. But the short version is I
The
came up with
summary, just
mostly
a summary.
yeah. Mostly that a lot of the data is not as good as we want it to be in terms of the magnetic field strengths, and so a big part of the dynamo theory is trying to predict how strong the magnetic fields are, and the measurements of the magnetic field strength and the estimates from dynamo theory just don't fit at all. But I mean, part of it is that getting the magnetic field strength requires a lot of assumptions that aren't always very good. So I contend that the magnetic field strength measurements are bad in a lot of cases, especially the ones from the 80s where the data wasn't that good. So we need better data. But one of the big results from my master's thesis was that the geometry, so like measuring like the spiral, how spiral the magnetic field is, for example, those measurements are very reliable and actually do work out well compared to predictions from dynamo theory. And I think that's because measuring like the pitch angle, like the how steep the spiral is, that's just geometry. I mean, it's just measuring angles. You're not trying to do very complicated physical calculations. And so the measurement is easy because it's geometry. And then the dynamo theory, is complicated, but it actually kind of works. And so the dynamo theory can kind of predict how steep the spiral is going to be.
That's not the
Moderately
strength
well.
of at the points of the spiral itself.
No, exactly that. Yeah. And so, but I mean, there is not just one dynamo theory. And so I showed, for example, in the case of galaxies, I showed this diagram of this is called the alpha omega dynamo, the alpha omega thin disk dynamo. And so there's some assumptions in this that probably aren't quite true. And so there are other competing dynamo models as well. So I know there's something called an alpha squared dynamo, but which involves this sort of convection and Coriolis property more strongly, or uses it for both directions, I think. There's other kinds of dynamos as well. I mean, a lot of the basic dynamos are so-called thin disk approximations, where they just treat the galaxy as though it were incredibly thin, when we know it's not actually. I mean, galaxies are pretty thin, but they're not infinitely thin. So
Right. Yes.
there's assumptions that aren't true, and so that means the models aren't completely true. And so the question is always, are these models okay? Like, how good are they, and how quickly do they go wrong? Are interesting questions, because we like to start with something that we can solve, that we can come up with analytic solutions for. And so some of these thin disk equations, thin disk models, you can actually solve them analytically or pseudo-analytically and write down equations for them. And so, a lot of interesting work on, okay, we have a model that we know is not perfect, but how good is it? How well can we get away with these simplifications is a big question.
Also, in this image suggests that there is radial motion of plasma, right? Because the magnetic fields are like X-shaped, you said.
Yeah. So yeah, this
So
becomes
it's
an
more like
interesting problem in the sense. It becomes a problem in the sense that in this environment, the magnetic field is. So I mean, yeah, in this case, yeah, the magnetic field will guide individual particles, like cosmic rays, for example, will stream along these big magnetic fields. But the bulk material, the majority of the material is dominated by the rotational motion, and so it won't get pulled radially by a significant amount, because there is this messy interplay between what is stronger, the forces, is the material dragging the plasma, is the plasma dragging the magnetic field, or is the magnetic field dragging the plasma? That's always a very classic question in plasma physics. And the answer is it depends on what kind of regime you're in terms of density and magnetic field strength and stuff. You can have either case occurring depending on the conditions. And so galaxies on large scales are a case of the material, the plasma, as it's orbiting, is dragging the magnetic field with it.
This image suggests that there is a general tendency for a particle to move diametrically, right? Not exactly,
Did you
but
repeat that?
there are enough parts. So this image suggests that there is a general tendency for the plasma to move diametrically, right?
I mean, if the plasma were being confined by the magnetic field, that would be true. But in the case of galaxies, that's not the case. So, yeah. On the bulk scale in galaxies, the magnetic field is pulled by the plasma, and so the magnetic field can influence plasma on smaller scales, on sort of like single parsec scales, so just tiny localized environments within a galaxy. But when you consider sort of the big scale, gravity wins.
Also, in future, if you're comfortable, like we can do a talk on like going from like MHD equations to this. That would be fun.
I don't think I have the the specific knowledge to really be able to do that. So, I put in the MHD equations in the talk, but I have never actually solved them myself. Like I've never done that
So
kind of
do I
work.
not need like MHD to get this? Oh, these are just observational data anyway.
This is observational data, yeah.
Yeah, I see. So I think like
And
that's
so,
good. We would conclude the talk now. Or anyone has any other question?
If you can just provide us with the source from where you took those MHD equations, it would be nice.
yeah,
To study the whole thing, maybe.
I'll post the slides, but
no, the slides are okay.
yeah,
Like those equations must have come from somewhere, right?
Yeah. So
Since
I have
they're
the image
number
created.
2 point something, so they might have come from somewhere.
Yeah. No, this is a set of lecture notes from a summer school on dynamo theory. And I think this particular set of lecture notes is from a professor in Newcastle that I've worked with. Got a professor by the name of.
Are they available publicly, or do you have them?
I mean, I downloaded them in order to take the screenshot. So yes.
Oh, okay.
I didn't go to the summer
if you
school,
can just write down the name, maybe like somewhere in whiteboard or somewhere in the server.
I mean, let me. Yeah, I can try and find it here. So.
Yeah,
you can just show it to me, so like I can download it and share it with everybody.
Also, I think like this time around, we will make a GitHub repo for each talk, so we can like have the resources in a one repository. Right? It would be nice.
Oh, this is annoying. So yeah, now that I see it, I'm remembering. So these lecture notes were actually published as a book, and so yeah, it's like $100 Canadian, which is annoying. And so there's like a few pages of it available on Google Books, and I think that's where I got the screenshot from. Annoyingly, is right. They have a table of contents, and then which is it's a very long book. It's hundreds of pages, but. And then, there are some. Oops.
Yeah. You just scroll. Yeah. Yep.
So there is some material. So yeah, it looks like found. There's a chapter here on foundations of MHD. So some of this is available, but the whole book is $100. So that's annoying. But I can link this in the chat, I suppose. But yeah, I'll post my lecture notes right away as well.
Yeah, so I'll make a repository. Is that fine? Like,
yeah.
Also, thanks, Cameron, for like I really enjoyed the talk.
Yeah, my pleasure. Yeah. All right. In that case, I will. Yeah, I'll post my notes and then I'll sign off for the day. So, thank you for coming.